If the sun fires a massive coronal mass ejection directly at Earth, we will have exactly 13 hours to prepare. Our Sentinel spacecraft monitoring solar activity will detect the anomaly immediately. They'll measure an ejection matching the scale of the 1859 Carrington Event. In 1859, that level of solar energy produced brilliant auroras and caused telegraph lines to spark. Today, that exact same energy is heading toward a completely electrified, highly interconnected global infrastructure. We rely on a constant flow of electricity for water distribution, financial networks, and global communications. That dependence creates a vast, exposed target. 13 hours is not enough time to reinforce those systems or stop the storm. It is simply a ticking clock leading down to the ultimate stress test of our infrastructure. The modern global power grid is built almost entirely to run on alternating current, or AC. When a severe solar storm hits, it forces massive amounts of direct current into the Earth's surface. These are called geomagnetically induced currents, or GICs. Like any current, GICs seek the path of least resistance, directly up through grounded neutral wires and into the electrical grid. Sensitive AC components cannot handle DC saturation. The DC current overwhelms the system, causing the hardware to immediately and dangerously overheat. Because we designed our power infrastructure without defenses against massive DC surges, the grid itself effectively acts as a giant antenna, collecting the energy that will destroy it. At T0, the storm's energy physically collides with the Earth's magnetic field, violently warping the protective shield around the planet. In the upper atmosphere, the sheer force of the energy strips molecules of their electrons. This sudden influx of free electrons instantly kills high-frequency radio communications across the sunlit side of the Earth.
Further up in orbit, the distorted atmosphere blocks GPS signals, cutting off vital navigation systems. Losing GPS disables precise timing applications that synchronize the global supply chain and international financial transactions. Before a single terrestrial power line feels the impact, the invisible digital synchronization holding modern society together completely evaporates. At 2 hours past impact, the full force of the geomagnetically induced currents pushes through the soil and bedrock to the surface. The grid's primary bottleneck is here: extra high voltage, or EHV, transformers. These heavy-duty components are forced to absorb the massive influx of DC energy. We know exactly what this looks like. During a smaller solar storm in March 1989, a transformer at the Salem nuclear plant in New Jersey was critically damaged by a GIC overload. The DC current overloads the system so severely that the copper windings inside the EHV transformers literally melt from the inside out. If a Carrington-scale storm hits the U.S. eastern seaboard and Midwest, these transformer failures will instantly cut power to between 20 and 40 million people. This is a physical burnout of the grid's most vital organs. A blackout caused by melted hardware cannot simply be rebooted. At T+24 hours, local terrestrial backup generators run out of fuel, and the crisis extends to the ocean floor, where long-haul cables carrying global internet traffic reside. These submarine cables stretch across continents, relying on electronic repeaters spaced every 50 to 150 kilometers to boost the data signals along the route. The extreme magnetic fields generated by the solar storm easily compromise these deep-sea repeaters, shorting out the electronic components that keep the data flowing. Once those cables fail, isolated regional power outages become a global communications collapse, digitally severing the continents from one another. With the physical hardware destroyed, the immediate aftermath shifts to the mounting financial cost of a dark, disconnected world. This presentation slide details the estimated impact. Every single day, the North American grid remains down. Between $20 and $40 billion in economic activity is lost. This chart maps longer-term projections. Lloyd's of London risk models estimate the total economic loss to the United States alone could reach $2.6 trillion over 5 years. Under extreme global scenarios, worldwide damages could reach $9.1 trillion. That financial toll eclipses any historical natural disaster, severely threatening the stability of the global economy. The reason the financial cost climbs so high is the recovery timeline.
It is impossible to simply repair the damage and turn the power back on within a few days. The destruction of extra high-voltage transformers creates a massive supply chain bottleneck. Currently, there is only a 33% spare capacity of these units worldwide. It takes 5 to 16 months to manufacture the replacement components, ship them across the globe, and install them on site. This process will be slowed to a crawl as every country on Earth competes for the exact same parts. This leaves society facing an arduous recovery period. Entire regions could spend 1 to 2 full years without access to reliable power or internet. According to astrophysicists, there is up to a 12% chance of a Carrington-scale storm striking the Earth within the next decade. We have the spacecraft and the forecasting tools to see the next storm coming, but until we physically harden our grid to absorb the impact, we remain completely at the mercy of the sun.